developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The optical properties of metal nanoparticles are one of the strongest light-matter actions known. Historically, they color ancient glasswork and today are the basis for numerous biological sensing devices. The Air Force is very interested in using these materials for various optical technologies. Unfortunately, their cost is not set by the noble metal nanoparticle, but by the orders of magnitude greater cost of the process to fabricate and integrate into different technologies. One of the hurdles to overcome is the development of alternative surface functionalization chemistries that are compatible with the reagents and concentrations used for the initial nanoparticle synthesis.
In this project, we are working to improve the scalable manufacture of functional nanoparticle materials. So first, a little bit of background. While nanomaterials have been around for a long time, they are still primarily made from noble metals, things like gold and silver. The great thing about gold and silver is that they're very unreactive. And the bad thing about gold and silver is that they're actually very unreactive. And so if you want to impart a specific functionality to these nanoparticles, you have to be able to put molecules on the surface of the nanoparticle. Traditionally, the scientific community and the commercial communities have exclusively focused on one type of attachment chemistry to do this, something called thiol chemistry. So in this type of chemistry, you attach molecules to the gold surface using the sulfur-gold bond. And this chemistry is known to have some pretty significant drawbacks. One of the problems is it limits the type of molecules that you can actually attach to the surface. And another problem is that the thiol-gold bond is known to be what we would call labile, meaning it's not super stable. And so, these surfaces can degrade even under exposure to atmosphere. So for about a decade now, my research group has been exploring alternative functionalization strategies to complement these existing thiol chemistries. In particular, we are trying to attach molecules to the surface using a gold-carbon bond instead of a gold-sulfur bond. What's good about that is that the gold-carbon bond is quite a bit stronger than the gold-sulfur bond, and these surfaces have been shown to have much better stability and also chemical tunability. So we are trying to transition our currently lab-based methods to the scalable synthesis of gold nanoparticles. Ultimately, we'd like to be able to make kilogram quantities of these things so that they can be used for advanced manufacturing or other applications that the Air Force is interested in.
We have been following a three-step approach where we first aim to functionalize our gold nanorods with N-heterocyclic carbines, or NHCs. Shown here is an NHC with an ester backbone that can be used for post-synthetic modification. In step 2, we aim to form a polymerization precursor with amide coupling. Shown here is an amide coupling with 4-vinyl aniline that will be used as a polystyrene precursor. By taking this approach with an amide coupling, we are able to form a modular precursor for our polymers in the future. In step 3, we aim to polymerize off of the gold nanorod itself by using a radical polymerization approach. As part of our current progress, we have also shown that a mixed monolayer can be formed on the gold nanorod surface. This was demonstrated by using 2 different carbines, one with an ester backbone for a functional group, and one with no functionalization at all on the backbone. Next, we wanted to demonstrate that we can post-synthetically modify our carbines on the gold nanorod surface. For this, we hydrolyzed the ester backbone functionalized NHC to the carboxylic acid. After the hydrolysis of the methyl ester to the carboxylic acid, we were able to complete step 2, where we showed that a polymerization precursor can be added to the gold nanorod with an amide coupling.
Towards that end, we recently achieved our first milestone on this road. We showed that we can do ligand exchange on commercially available nanorods, and this work was recently published in RSC Advances. And I think this is the first step towards actually scaling these materials and being able to tailor them to the properties of interest.
John's team's carbane-based chemistries are an exciting development that may address this age-old challenge. Our collaboration working out the limits and developing concepts to enhance the tunability, coupling efficiency, and maintaining generality to numerous nanoparticles have been very exciting and promising. The initial proof of concepts that have been developed with his team have identified follow-on opportunities to continue development of these ideas for a couple Air Force R&D priorities.